excited about this talk because I pinged Carlos about soil acoustics maybe 12 months ago because it came up as one of the topics in Bill Sutherland's Horizon Scan last year. And I got messages asking me, is this even a thing? And I had no idea. So I asked the person who would know, which was Carlos. And here we are, full circle. Carlos has come to talk about soil ecoacoustics. So I'm very excited. But let me just introduce you like formally. Carlos Abrams is the Director of Ecoacoustics at Baker Consultants and a Senior Lecturer at Nottingham Trent University. He works in bioacoustics and ecoacoustic survey and monitoring methods, particularly for birds, freshwater habitat, soils, and general soundscape assessment. I think we've had you on to talk about freshwater acoustics before.
And birds, yeah.
And birds. Oh my goodness.
I think, yeah.
Okay, all right. Well, yeah. third time's the charm.
The charm, maybe. This will be the good talk, I think, yeah.
All right, go on.
Okay, thanks, Steph. Hi, everybody. Thanks for having me. Steph was saying I'm here to talk about soil acoustics, and in contrast to the two previous, this is the cheap, dirty, and very undeveloped bit of ecoacoustics, really. I've done a bit of work on soil ecoacoustics, but not alone in doing that. So I'm just going to quickly mention some of the background and other people you really want to look up for the limited amount of research that's been published on this. So Ollie Metcalf has done work in the Amazon. If you're into Amazon soils, then he's the guy. Jake Robinson, who we did a bit of work on a couple of years ago in Sheffield in the UK. He's now based in Australia and has done a bit of field study there, and in the last couple of days has just brought a review out in the, if you look up Jake Robinson and soil meta review, you'll find his work that's just come out in the last couple of days in terms of looking at recording biota. Marcus Mader in Switzerland, who's really kicked the whole ecoacoustics thing off 3 years ago or so. And then there's a sort of history going back with sound recordists like Jez Riley-French and other people who've looked more at soil bioacoustics and pest management and control and detection. So a guy, Richard Mankin, who's based in Florida as well. So the recording stuff underground has gone back maybe 20 years or so, and probably longer. But a lot of that's been quite focused on small species groups, and the ecoacoustics and the broader sort of use of environmental sounds studying within soil has only really come out since about 2020 or even later than that. So it's pretty fresh, pretty new, and because of that the methods and the hardware are in development still. So in terms of soil sounds, you can record a variety of sounds: anthrophony, geophony, whatever, so man-made sounds and natural sounds as well, but there are some biological produced sounds that you can record in soil. A lot of that is just the banging and crashing of things moving and feeding as they wriggle around in the soil, but some taxa, and beetle larvae probably especially, do produce intentional stridulation sounds, so they sound like underground crickets, and if your mic is close enough you can hear them, and hopefully this should play. It starts off quiet, but the volume increases. So it's not the most exciting of sounds, maybe, but as I say, some of these coleoptera and other invertebrates, ants and some other things, produce sounds. They have stridulation features either on the legs, torso, or the mandibles that they produce sound with. And for the 3 species that have had some work done on them, they do seem to be species specific. So we can tell which beetles, as far as we know, are present if we can record their sounds well enough. Recording their sounds well enough is the tricky bit, though. As well as recording those intentional sounds and taking sort of a bioacoustic approach, we can also take a more ecoacoustic approach. And so some of the work that's been published by Marcus, myself, Jake, and Ollie has used acoustic indices. So some of the crowd's probably familiar with these, some may not be, but this is basically looking at rather than trying to identify characteristic sounds from animals that we know, we're just getting a measure for the diversity and complexity of the sound that's we're recording in the soil. And we can see, if you look at the coloured graphs on the right hand side, that we do get patterns in those acoustic indices during the course of the day. So what tends to happen is that the soil becomes more noisy as the day warms up during the middle of the day, and becomes more quiet again in the evening. So it's related to soil temperature, and we can see similar patterns during the course of the year. So there are seasonal as well as diel changes as well. And if we look at those acoustic indices, we can relate them to the diversity and number of soil animals that are there. So whether this graph on the left hand side is from Marcus Mader's paper back in 2022, where they took soil cores out, funneled all the invertebrates out, looked at the diversity of those, and compared that to the acoustic complexity index, and you get a pretty good relationship between the two. So the more diverse the soil fauna is, the more diverse the sound is, and so we can use acoustic indices to get a handle on soil biodiversity, which is really useful, because the only other two ways to measure soil biodiversity at the moment are to spend lots of money doing eDNA, high throughput, metabarcoding, whatever. I don't understand it, I can talk about it in broad terms, and measure stuff like that. Or we can take a spade out, dig the soil out, and count the number of worms in. So at the moment there's high tech, low tech, cheap, yeah, and backbreaking or expensive and high technology, and soil acoustics fits pretty well in between those in terms of a scalable technique that's easily implementable and scalable across large areas, and shouldn't cost a lot of money to do. So it's a good intermediate technology. So talking about intermediate technologies, and Mona just given us all of this stuff about brilliant wildlife acoustics kit, which has been developed over a long period of time, and the fiber optics under the sea is also really good. At the moment, we've got pretty much no idea of what an optimum system for recording soil acoustics is. We can take soil recordings using a variety of kit, but no one has really done any testing to see which system is better than others, which materials and which recordings. But basically, we need a decent recorder, and then we need a sensor that is plugged into the soil in somehow. And there are different ways to doing that. So I'm going to go backwards and start at the right hand side of the screen here. One solution is to dig a hole, stick your recorder, whether it's a contact microphone, hydrophone, condenser mic, potentially, bury it underground, fill the hole back in, and then record sounds produced from there. That has been done by a few people. Ollie Metcalf's paper from the Amazon used this approach. The problem with that is that you disturb the soil that you're trying to record, and it's okay for long-term deployments, but if you wanted to record spatial replicates rapidly across a landscape, you can't be digging the soil up every time you want to do that. The other approach, going to the middle, is to put a sensor on the actual ground and see if you can pick up vibrations coming to the soil surface. That's been used again in some military applications, for example, to listen for tunnels on the battlefield. But in terms of recording invertebrates, maybe not that great, and you need quite a clean surface, because to get good coupling between the microphone and the soil, if you've got vegetation in the way, again, that's another issue. So the left-hand solution is the one that myself and other people in the past have used, and that is basically to stick a probe into the ground. And the probe, which is metal spike of some sort, picks up the vibrations that are produced by the invertebrates in the soil and transmits those out of the soil to a sensor that sits above the ground. And so if you can imagine taking a knitting needle or a 9-inch nail or a piece of rebar, which have all been used for this solution, stick that into the ground, clip your mic to it, then this works as a good, easy to deploy solution. And one that's been used by quite a few papers. But in terms of how that works in terms of the material and shape and size and those sorts of things, those optimum solutions haven't been suggested yet, or haven't been found out. So ourselves and others have tried different materials, different sorts of tent pegs in different types of metals. Some lab papers have also used glass probes for this, that they detect the microphone too as well. If you look at Marcus Mader's work, he prefers gold-plated copper wire. He comes from Switzerland though, so there's probably plenty of gold available in the coffers there to use that. We tend to use 2mm steel wires that go into the ground, and a little bit of testing that we've done on this shows that actually which material you use doesn't make a great deal of difference probably, and it's the size, length, and how well it couples to the soil and how well it couples to your mic are probably the more important things than actually what material it's made out of. Ourselves and others have done a little bit of testing in terms of how these waveguide, these probes should be, whether the width, the mass and the length makes a difference. Nobody knows. Nobody's published any work on that at the moment. We've got a few vague ideas on what we prefer in terms of that. And then in terms of cross-section shape, is just a narrow wire good, or actually if you've got more surface area, some of the original pegs we used were sort of triangular shaped tent pegs, which got really good contact with the soil in terms of the surface area, but were pretty much impossible to get into hard vineyard soils in the middle of France because the ground's too hard. So we tend to prefer narrower, thinner ones. So ourselves and other people have done a bit of testing of this, but none of this has been published at all so far. So actually in terms of what is the optimum material, shape, size, length and everything else for a waveguide, nobody knows. And physicists, don't like to pin their colours to the mast on this as well in terms of what's best. So nobody really knows at the moment. So the bit that goes in the ground, we can argue over what that should look like. In terms of the actual sensor bit, most of the work that's been done on this has been done with piezo contact microphones. Some people have used hydrophones in the past and buried those. Some people have used accelerometers also as well, which are quite spendy, and the information can be quite useful. It's slightly different to interpret in terms of an acoustics signal though. So I'm going to sort of park those on the side at the moment and concentrate on the other things. Because of the availability of contact microphones, most of them tend to use these circular disc type things that you can buy off eBay for about 20 pence each, or you can buy slightly better ones from people like Xavier French or Shirtler and spend £70 or £40, £400 or whatever, depending on your budgets. However, the same sort of material is also available as a piezo film rather than a round disc. And it's also available as a piezo cable as well. Nobody's really tested these that I know of, apart from myself and Marcus Mader. And so when you think about taking a probe object, I'm holding a pen up just because it's a long pointy thing, and trying to connect a piezo sense to the top of that, if you've got a 2mm wire, does having a round disc that's about 1 inch across and hardly contacts the wire the best option, or would a narrow thin bit of piezo film be better? Or could you actually embed some piezo cable within a metal tube that goes into the ground and potentially pick up vibrations there? Fairly similarly analogous to the fiber optic solution that Martin was talking about not long ago. So yeah, standard contact mics, they're pretty cheap, they work, and so we can get answers out of those at the moment, but are they the best solution? I don't know, nobody else does, so somebody needs to find out really. Other things that we need to think about when recording in the field are getting strong enough signal. The signals that we pick up in the ground tend to be quite short range. The soil is a very good filter, low pass filter for sounds, and sound doesn't travel very far through it. So a detection range for most invertebrates that we're trying to pick up is probably in the region of about 50 centimeters radius from the sensor. It's very short range stuff. Higher frequencies get lost super quickly as well, so it tends to be the lower frequency stuff that we do. And contact microphones, those piezo film have very high impedance, which doesn't match very well to low impedance recorders. So you need a good recording unit with really good signal to noise ratio. So the more you spend on the recorder, the better. You probably need a preamp to boost the signal, and if you are using a contact microphone with high impedance, you need an impedance filter, otherwise you're cutting out all of the frequencies below about 250 or 500 hertz. You also want to try and protect your above ground sensor from background noise, wind vibration and contact with vegetation as well. So we take the super high-tech solution of putting a silicone bucket over the top of the microphone when we're doing field recording. And so, yeah, it's the other end of scale from a 250 kilometer fiber optic signal, I think, in terms of what we're doing, and we're still trying to work out what is the best system for that. And so to finish off, I need to plug this. We are currently working with soil scientists at Warwick University in the UK. We have about £350,000 worth of grant from UKRI, and are doing a few things with that. We are developing a prototype for a farmer-friendly soil acoustic recording device with one button and a single probe that's GPS linked. So landowners without any technical capabilities whatsoever can take recordings, standardized recordings from the field, and then upload those to our website that's on its way to do the analysis for them. As part of the work to back that up, we are developing a sound library. So we've got a couple of thousand soil recordings from farmland across the UK at the moment that we're developing machine learning and acoustic index parameters from. And also doing lots of recording of worms and other invertebrates in buckets as well, to see if we can develop ML tools to detect some of the species. So we've got sort of a range of experiments going on, from very small scale mesocosms to the landscape stuff across the whole of the UK, to try and get some data together to start to understand how to record soil sounds, how to interpret them once we've got them, and make that available to farmers across England, which is what our grant's for, but also conservationists and researchers and everybody else, to try and start listening to soils and making use of that for conservation and ecology research. And I'll finish there. Thank you.
That's awesome. So I guess you had a lot of comments and suggestions in the chat, so I definitely will pop you into the chat to look at them. But I guess there was one question that came up in registration. It came up a couple of times in the chat, like, so, and I can see that you're working on it now, but how far away is just off the shelf tools for monitoring soil acoustics, and to get to the point where they're ready to assess soil organism abundance and diversity? How far away do you think it is?
We are doing the research. We're also doing some trial projects for some landowners in France and the UK at the moment, and so the acoustic index type of thing, we can record pretty decent field data recordings and can analyze that, and we are starting to develop an understanding of how that's related to land use, for example, and what the natural scale of acoustic indices are within soil and the amount of variation. And but at its simplest level, the more sound that is going on, the better the soil quality is, soil health is, however you want to talk about that. And I say at that level, our ambitions are fairly low. We want to be just slightly better and slightly cheaper, easier and quicker than digging worm pits, which is the current standard for assessing the soil health.
So Carlos, do you think it's like 5 years away or 10 years away, or
we're hoping to have our product out, the hardware product and the analysis website sometime, I'd say not for Christmas, maybe early in the new year, so pretty soon.
Oh, okay, really soon. Okay, cool. Interesting. Okay.
But and then the next level from that then will be interrogating that sound data in more detail and linking it expressly to, say, if we've got this acoustic index in this location, how does that relate in any way to, yeah, worm numbers, for example, or other invertebrates?